In this next section, we're beginning chapter 30. This section is on induction. The first part of this chapter is on an area called self-induction. And in order to understand induction, we must remember what we had in the last chapter with Faraday's law. And so I'm going to briefly remind you that with Faraday's law, we learned that if we have a changing magnetic field, here's the time derivative of the magnetic flux through an area, it creates a voltage. So if you have a magnetic field that changes in a given area, it creates a voltage, and that voltage will cause a current to flow. The current then in turn causes a magnetic field as a result of the flow of the current, which we've learned also. Now, addressing induction. Self-induction is the change in a current when a wire creates a changing magnetic field and thereby creates an induced current, which in turn opposes the voltage that creates that original current. Now, what does that mean? It means, like, let's imagine we have a wire, and this wire has some current flowing in it, and as a result of that, you can see that we would have a magnetic field, and it would go around in this direction as the current came around here. Again, by the right-hand rule, if we put our thumb along here, the magnetic field would go over the top and into here. And if this current changes, then the magnetic field changes. And this is the magnetic field B. But if the magnetic field is changing through this area, then by Faraday's law that we've just learned, that creates another current. Well, that current is going to go in the opposite direction or oppose. This is the induced current. The induced current. And it's going to flow in the opposite direction and therefore oppose the change that we had, because this is going to create a magnetic field in the opposite direction, which would go beneath and come up the top, a magnetic field in this direction. Self-induction is this induced voltage, and it turns out that the induced voltage, V, due to the inductance, is negative, and the negative sign comes from the fact that it is in opposition to the number of turns we have times the change, the derivative with respect to time, the change in the flux of the magnetic field. Now, the flux in that magnetic field can come from changing the shape of the wire, so that changes the flux, or it can come from changing the current that goes through here. But however it's done, if the total flux through this wire, through this loop, changes, then in fact we will induce a voltage itself, so that we have a self-induced voltage. Again, where can this voltage come from? We can either try to change the amount of current that goes through here, and therefore that will change the magnetic field, or we could even change the shape of this object. For the time being, we're not going to worry about changing the shape. We're going to worry just about keeping exactly the same shape that our wire has, and in fact changing the amount of current that flows through. And so if that's the case, it turns out that for a fixed geometry, this is going to be minus a constant times the change in the current, I, with respect to time. Now, the unit of inductance, and this is inductance right here, is the Henry. And you can see what that would be. It's a volt over here, change in amps over change in seconds. So it's going to be a volt times a second divided by an amp, and that would be a Henry. Henry is the unit of inductance. And here we're looking at self-inductance. So if we try to change the current, the system is going to oppose it. That means if we try to reduce the current through a loop, it tries to increase it. If we try to increase it, it tries to decrease it. And that's what this negative sign is right here. So it's difficult to compute the change in flux, but we know that it's due to the change in the current. Every electrical current is in some form of closed loop. because the electrons have to flow around and come back to where they started from. And therefore, everything has some kind of induction, self-induction. So the voltage across an inductor gives the last component of what we call the RCL and voltage, resistor, capacitor, inductor, and voltage current components that we need to discuss electrical currents in general. This is our main formula. Voltage inductance is equal to minus L di dt. So if we had a problem where we had a circuit that had a self-inductance of 4 henries, and we tried to change the current, so there was a change in I of 6 amps in a time, delta t, of 2 seconds, then we would have that the induced voltage would be 4 times the change in I, that would be 6, divided by 2. 2 into 6 goes 3, 3 and 4 is 12, so this would be 12 volts. It'd give us exactly 12 volts in that type of circumstance. Now there's a negative sign here, and that negative sign simply means that this voltage is in opposition to the voltage that's causing the current. This is the concept of self-induction. We'll learn later that one circuit can influence or produce an inductance in another circuit. But right here we're just looking at the effect of a current on its own self.